Welcome to the 7th week of this course. In the last week we started with analysis of composite laminates and we did static analysis. In this week we will do buckling of composite laminates. Now before going to the buckling of composite laminates, let's spend few minutes in understanding buckling. Now buckling is a static stability. Now stability is easily understood with the help of this analogy. So let's assume that we have a terrain like this. Now and this terrain is under a gravitational field. So if you put a ball here and this ball maintains equilibrium here. Now if we displace the ball to a new position somewhere here, and then after that if we leave it as it is, the ball comes down. Similarly, if we keep it here and then leave it, it again comes down. So this ball has a tendency to retain its initial position, this position. So this we can say that at this position this ball is in equilibrium. The same thing will happen if we keep it here. But on the other hand, if we keep the ball here and then if we just displace it little bit and leave it, it will not come down to the original position. Rather, it will move far away and come somewhere here and try to find a position here. Or if I displace it toward this side, it will do the same thing. So we can say that this ball is not stable in this position. It can be in equilibrium, but it's not stable. So this is its stable equilibrium and this is unstable equilibrium. So ball does not find stability here, rather it finds stability here and here in these two sides. Now if this is under gravitational field, we can say that at this position when it is in equilibrium, at this position or at this position, here the gravitational potential is minimum with respect to the surrounding positions along the terrain. On the other hand, at this position where it is unstable, we can say that the gravitational potential is maximum with respect to the surrounding locations around the terrain. So the takeaway is that minimum potential energy indicates stability and maximum potential energy indicates instability. Now there is another possibility here, that is if the ball is here, if I displace it and if I keep it here, it will neither go back, it will neither go forward. That means it's just neutral. So wherever I place it, it can be there. It does not show any tendency to go back or go further forward, and this is called neutral equilibrium. So here with respect to the surroundings, everywhere the potential energy is same. Now let us come back to a structure. So let's look at a column, an axial member under some compressive load. So let's assume that this member is under compressive load. Now when the and we can draw a simplified diagram of this here. A straight compressive member under compressive load. If we want to keep it look same, we can just reduce the length little bit. So maybe like this. So it's under compression. Now when the load is not so high, this initial straight configuration is its equilibrium configuration. That means if I give a force here, transverse force, it bends and looks like this, and after that if I remove this force, it again comes back to the original shape how it was before. That means it's a stability. It has a tendency to this axially loaded column has a tendency this axially loaded column has a tendency to go back to its original straight shape. But if we increase the axial load gradually, then after some value of the axial load, this initial straight configuration becomes unstable. That means again it was like this. If I give a load, it bends, then if I take the load back, it does not come back to the original position. So there is a permanent deformation. What it means is that the initial straight shape is not its equilibrium configuration now under this axial load, rather this shape or this and this shape, these are its new equilibrium. So this the original straight configuration is not its stable configuration now, rather this shape shown by this dashed line or this shape, they are now its new stable configuration. So this is stable configuration, this is stable configuration, and this one is unstable configuration, and this phenomena is called buckling. Now when there is some imperfection in terms of the load being little bit eccentric, or the column having little imperfection, which happens in real case. So we see that's what causes the onset of buckling, and when and because of this straight configuration being its unstable configuration, we see this buckle deformation here, the permanent buckle shape. If we say that everything is ideal, that means my load does not have any eccentricity, the column does not have any imperfection, that is like somehow balancing this ball here. Apparently it looks fine here, but the moment some disturbance comes, even a very minute disturbance, it can shift it from this point to this point or this point. So in that case, in an ideal situation, there may not be any visible deformation, visible transverse deformation, bend shape, but then if we give a little bit of disturbance, it just takes this shape, this shape or this shape, depending on which direction the disturbance is. So when we do analysis for buckling, our main goal is to find out the critical value that causes buckling. So in this case is P less than P critical, that means the load is not that high to cause buckling, and in this case the load is more than P critical. So for a structure there is a value of P critical, and when the load exceeds, the axial load exceeds that P critical value, the buckling is caused. Now generally we impose this problem, mathematically we formulate this problem as an eigenvalue problem. So the eigenvalues are the different critical loads, and the eigenfunctions or the eigenvectors that we get, they signify the buckle shape. We call it mode shape for buckling. So for this problem, a column hinged at both sides, the P critical value is n square pi square EI by L square. E is the elastic modulus, I is the moment of inertia, and L is the unsupported length, the length between the two hinges. So we can call it PCRN, that means nth critical buckling load. So when n is equal to 1, it is pi square EI by L square, n is equal to 2, 4 pi square EI by L square, and so on. So when n is equal to 1, this is how the buckling shape looks. It can be in this direction also. So these are the two shapes, and the initial state configuration is this. N is equal to 2. Again, this is the initial state configuration which is not stable now, and the buckling mode shapes are this. Now here one thing to note is that this P, when it is compressive, that has a destabilizing effect. That means if I study the effect of it in a bent configuration, this force P due to this offset causes a bending moment in this direction, which tries to add to its bending tendency. On the other hand, if this P is in the tensile direction, in that case this moment is in the opposite direction and it tries to straighten it. So a compressive force has a tendency to destabilize. Now when the destabilizing effect of that compressive force overcomes the stabilizing effect of its own stiffness, then we can say that it is going towards instability. Now we will go and study, we will go to study the buckling of plates, the laminated composite plates. Now when it is a plate, there are two dimensional effects. So the load that is causing buckling, it can be a compression along one direction, it can be compression along two directions, and also there can be shear associated. So individually they can cause buckling, or there are certain combinations also can cause buckling, and we will study that. Now the first step is to write the governing differential equation for buckling. Now previously we have seen that these forces, the in-plane forces, the compressive force has a destabilizing effect, and we can only see that effect when I see this column at a deformed configuration. If I see the initial straight configuration, I cannot see the moment due to the column. So to visualize that moment, to have that moment in action, we need to have some deformation in the column. Similarly, in the plate also the same thing. So that's why when we write the governing differential equation of for buckling of the plate, we need to see the equilibrium of different forces in the deformed configuration, not in the original flat configuration. And that's how the difference comes between what we did previously in last week and this week. In the last week, our goal was to study the static deformation, and we wrote the governing differential equations. For writing the governing differential equation, we studied the stability of the flat plate, initial flat configuration. But here we have to incorporate the effect of, the destabilizing effect of these shear and normal forces. So for that we need to study it. We need to see the small part of the laminate and its various forces in the deformed configuration. So that's how it is here. So in this diagram, these green lines, they show the axis x, y, z, and this plate, the small portion of the plate. So this is we take out a small portion of the plate and then we study here. So here we are seeing it in the xy plane, and here we are seeing a small portion of the plate which is this, and we are seeing it in xy z system in 3 dimensions. So we can see that this plate has some inclination with respect to x axis as well as with respect to y axis. Now these in-plane forces Nx, Ny, Ns, they act along the plate. So when the plate is inclined in the deformed configuration, these forces are also inclined. So because of this, they have a component along x axis, x axis or y axis, as well as along the z axis. For example, if we look here, so this is Nx, that means at the negative face of at the negative x face. So here the normal force is Nx, and again please understand these forces are force per unit length. So this Nx, it makes an angle here, and we can say that this angle is del w by del x. So this angle it is making with respect to x axis. Now here this same slope when we traverse this distance del x along the x axis, along this plate, there is a change in the slope with respect to x axis, and that new slope we can call del w by del x plus del 2w by del x2 multiplied by delta x. Similarly, if I look at this, this is del w by del y, and here we have the ny plus some increment, and the corresponding slope with respect to y axis is del w by del y plus del 2w by del y2 multiplied by delta y. Now let us look at the shears. So if we look at this shear force at the positive y face, it makes an angle with respect to x axis, and that we can write as del w by del x plus its increment. So we have to write the slope of del w by del x along y axis, which is del w by del x del y, del 2w by del x del y, and we multiply that with delta y. Similarly, here if I want to look at the slope of this shear force with respect to y axis, then we can write it as del w by del y plus increment the slope of this slope, so that is double derivative del x del y, and then multiplied by delta x. Now we know the orientation of different forces, their magnitudes. So now we can write the equilibrium. And just one thing to note, previously when we are doing the static analysis, there was a transverse force, but here we are doing buckling analysis, so there is no transverse force. So this is the same figure here, so we can refer to it. Now let us write the equilibrium along z direction. So this force nx plus del nx by del x into delta x, this has a component along the z axis, and that component is nothing but this force multiplied by sine of this angle, and this angle was del w by del x plus del 2w by del x2 multiplied by delta x. So sine of this angle. Now here we assume that these angles are small, that means the bend the slopes corresponding to this deformed shape is not so high. So if this angle is small, then sine of this angle is equal to this angle itself. So we can write nx plus del nx by del x multiplied by delta x, and then we multiply the entire thing by del w by del x plus del 2w by del x2 into delta x. This force that is tilted towards the negative z direction, so it gives a negative configuration, and the corresponding slope here is del w by del x. So we write minus nx into del w by del x. Likewise, if I see that this angle also we have seen before, it is del w by del y plus del 2w by del y2 into delta y. Again we multiply this with this to find out the component along the z direction, and that gives a positive contribution in y plus del ny by del y multiplied by del y into del w by del y plus del 2w by del y2 into delta y, and then this ny force is tilted towards the negative z direction, and the corresponding angle is del w by del y. Now let us look at the contribution of the shear here, ns plus del ns by del x into delta x. We know that angle, so that is ns plus del ns by del x into delta x, and that angle was del w by del y plus del 2w by del x del y multiplied by delta x, and the vertical component of this force Ns is minus Ns into del W by del Y. Similarly, if we look at the shear at the positive Y face, the shear is Ns plus del Ns by del Y into delta Y. So we have Ns plus del Ns by del Y into delta Y, and its slope is del W by del X plus del 2 W by del X del Y multiplied by del Y and minus Ns into del W by del X. So these are the vertical components of the in plane forces. Now there are out of plane shear forces Vx, Vy and the corresponding quantities at the positive x and y face. Now because we are looking at the deformed configuration, so the direction of those those forces are also not perfectly aligned to z direction, but if we assume that their inclinations are very small, in that case the cosine of those inclinations are almost equal to 1. So we can say that the z component of those forces are equal to those forces itself. So with that we can write, okay, so another thing to add here, so these are the forces per unit length. So we have to multiply this with the corresponding dimensions. So this force is acting at x face, so we have to multiply it by delta y. This is acting at y face, so we have to multiply with delta x, and this is acting at this face, so this has to be multiplied with delta y, and this has to be multiplied with delta x. So now they give the total forces. Now we have this vertical shear force Vx plus del Vx by del x multiplied by delta x, and it is acting at x face, positive x face, so multiplied by delta y, and minus Vx delta y, and here we have Vy plus del Vy by del y into delta y multiplied by delta x, and the negative y face we have Vy into delta x. Now all these things now is under equilibrium. So the summation of all these forces along z direction is 0. Now what we can see here is this Nx into this Nx into del W by del x is equal to, again here we have Nx into del W by del x with opposite sign. So we can say that this and this this with on being multiplied by this and this quantity cancels each other. Similarly, if I multiply this with this, then this is cancelled by this. Again this multiplied by this quantity cancels this one, and this quantity multiplied by this quantity cancels this. And similarly here this Vx into delta y, we have negative of each other, and same here. Now if we write down rest of the remaining forces, we get del Nx by del Nx by del x into delta x multiplied by del W by del x. So what we can do here is we can take these quantities outside, and it will be easier to write. So we get quantities like del Nx by del x So what we get here is del Nx by del x plus del Ns by del y, and that is multiplied with del W by del x, and then we have plus del Ns by del x plus del Ny by del y, and that is multiplied with del W by del y, and then we have plus del Vx by del x plus del Vy by del y, and then we have Nx into delta 2W by del x2 plus Ny into delta 2W by del y2, and then we have plus 2Ns into delta 2 by del x del y. Now these quantities are all multiplied with delta x delta y. So we have everything multiplied with delta x delta y, and that's equal to 0, and we know that this delta x delta y is not 0, so whatever is remaining, that's equal to 0. Now again within these quantities, this quantity is 0 we know from the in-plane equilibrium equation, and this quantity is again 0 we know from the in-plane equilibrium equation. So finally if we write rest of it, the equation that we get is del Vx by del x plus del Vy by del y plus del 2W by del x2 plus 2Ns del 2W by del x del y plus Ny into del W by del x2. Now we know from moment equilibrium that del mx by del x plus del ms by del y minus Vx equal to 0, and the other equation that we get from moment equilibrium is del ms by del x plus del my by del y minus Vx equal to 0, and these two come from moment equilibrium. Now if I combine these two equations with the equation that we got just now from the equilibrium of forces along z direction, then we can write dxx, let's not write in the form of d now, just write in the form of m, that's better. So del 2mx by del x2 plus del 2 twice of del 2 ms by del x del y plus del 2 my by del y2, and then we have plus nx into del 2w by del x2 plus 2ns into del 2w by del x del y plus ny multiplied by del 2w by del y2 equal to 0. So this is our new equilibrium equation. If we compare with the similar equation that we got for static analysis, then here we had the transverse load term. So here as opposed to that we get the effect of the in-plane forces. Now one thing, these in-plane forces, they are called membrane forces, and they are considered to be present in the pre-buckled state itself in the original flat configuration. And then further, if we assume that, or if we consider that the derivatives of these forces along x and y direction are not high, very small, then we can consider this to be the applied normal forces itself. So for that we put a bar sign there. So that means we have a composite laminate, or we have a plate which is under these forces. These are uniform forces, uniform nx bar, uniform ny bar, ny bar, and then it can be accompanied by applied shear ns uniform. Yes. So these nx we put a bar and denote that they are our applied forces under some considerations. Now if our if B is equal to 0, that means there is no coupling between in plane and out of plane deformation. In that case, let us call it equation number 3. In that case, equation number 3 is only used. However, if B matrix is non-zero, if any of the B is non-zero, is not 0, that means there is a coupling between in plane and out of plane deformation, then equation number 3 along with the following two equations are used for studying buckling, and those two equations are just in plane equilibrium equations, and those equations we already know: del n x by del x plus del n s by del y equal to 0, and we have del n s by del s plus del n y by del y equal to 0, and let's call it equation number 1, 2 and 3. So if B matrix is 0, we can use only equation number 3 for studying buckling, and if B matrix is non-zero, if there is a coupling between in plane and out of plane terms, then we have to use equation number 1, 2 along with equation number 3. So this brings us to the end of this lecture. From the next class we will start finding out the buckling loads and buckling modes using these equations. Thank you.